Good afternoon. This is a replacement lecture for lecture 11, and I'm recording it in September of 2019. This will be your first new lecture after exam one. And I'm going to try to make more replacement lectures as the semester goes. But uh, if I don't get them all done, we still have the regular spring 2019 lectures that are perfectly fine. This one is just streamlined a little bit without remarks that only the lecture hall students needed and stuff. Now, a few lectures ago, we talked about the interaction of skateboarders. It's in the very beginning of chapter 4, which is in the free textbook. And that was about, the gist of that was to talk about impulse. This is the impulse equation, F delta T equals M delta V. And this is an important concept because this is what Sir Isaac Newton was talking about with his three laws of motion. He used the term quantity of motion in like the very first page of his book, The Principia. Um, but nowadays we use the term momentum for that concept. Now for us, it's P equals mv, and the velocity, of course, has three dimensions. So the momentum has three different dimensions or components. The x component, p subscript x, the y component, p subscript y, and the z component, p subscript z. Now, normally we're going to, in this class, we're going to do fairly simple momentum problems. So we're always going to be, usually it's going to be the x component of the momentum, then the other two are going to be zero. But theoretically, this is what Sir Isaac Newton was talking about. And the reason I bring that up is because we have another dynamical concept in chapter 4 called energy. And the person that brought that into focus is Albert Einstein. He constructed a four-dimensional version of the momentum. And the nice thing about it is that when we talk about symmetries in nature, the dynamical symmetries that we find are in, sorry about that, unknown caller. Anyway, uh, when we're talking about symmetries in nature, the dynamical concepts that are needed are energy and momentum. So Albert Einstein put together a four-dimensional version of momentum. It has the three spatial components, and then energy is the very first component. And when when you're talking about Einstein, a familiar formula that many people have seen for energy is E equals mc squared. Now we're going to get to that at the end of this lecture. So this is kind of just a little flavor of where we're heading. What I want to talk about now is this, go back to this idea of skateboarders interacting and exchanging momentum. And we're going to have some homework problems. I think we may have had this one uh, as a homework assignment already. You observe two skateboarders interact as observed in lecture and as seen in various videos. And also as lined out in chapter 4, the very first part of chapter 4. In the lecture hall, the day that we did this, no, I take that back. In this one, Raymond and Gregory, Raymond for R and red, and Gregory for green. So this picture, Raymond is on the left and Gregory's on the right. And so this is a homework problem. Two snapshots show the positions during the interaction and a few fractions of a second after the interaction. The upper image is the last instant of contact, and the lower image is after some interval of time, delta t. So this one is This is the part of the image or the part of the problem that's immediately after the interaction of small delta t later. Okay, the mass of Raymond is 75 kilograms, and he travels 1.05 meters in travel time. Delta t equals 0.52. How much momentum does Gregory capture from the interaction? All right, so we can figure out that if we want. And that's a typical, we're getting more phone calls here. We'll just ignore the phone calls. All right, so let's get, so to do problems like this, sorry for the interruption, you want to think about the impulse equation. So let's focus in on it. The dynamical quantity impulse is, usually you refer to it as F delta T. Sometimes you see it in lazy textbooks as F times T, but I almost always will write it down as F delta T. Now that equals the change in the momentum. Okay, so the change in momentum is equal to the impulse. F delta P equals F delta T. And it's a vector statement. Now, most of our vectorness we're going to handle with plus signs and minus signs to indicate right and left. But yeah, that's a vector statement. And just to remind you, if you did your reading, you'll realize that this is just another version of Newton's second law, F equals ma. And I'll refer you to chapter 4.1 to reinforce that. Now, the main thing that I want to focus on with you is that the impulse formula gives us a very easy way of calculating a stopping time. Now, here's a homework problem that's coming up for us in one of our future homeworks. Given a coin of mass 0.05 kilograms sliding across a tabletop from left to right. At initial point x1, its speed is 1.7 meters per second rightward. Okay, so that's positive 1.7 meters per second. And it then experiences a frictional force of size F equals 0.020 newtons leftward. Okay, so when we write that down in an equation with other stuff, like the impulse equation, we'll write that down as negative 0.020 newtons. Okay, then below the sketch, below the diagram, it continues. It slows down to a stop at position x2. So V2 is 0. It's stopped. Question, what is the stopping time for this coin? Type in the numeric part of your answer to the nearest 0.1 second. Okay, let's go and take a look at some of the specs. Here it is, just rewritten. We're going to try to figure out the stopping time for the coin. And to do that using the impulse formula, we've got to have the force and we've got to have delta P, the change in the momentum. Delta T is the elapsed time. That's the stopping time. So that one we don't know, but we can figure it out from the force and the momentum. So first of all, let's get P1 and P2, and they're going to give us delta P, right? And the force on the left side of the impulse equation is 0.020 newtons to the left. And as I mentioned before, we're going to use negative 0.020 newtons in our impulse formula. You'll see it in just a second, to indicate leftward friction force. So the friction is always opposite the direction of the motion. So if you're moving to the right, from left to right, your friction force is back to the left. If you're moving to the left, your friction force is back to the right. So this one, the motion is left to right, so the friction force is the opposite direction. So it gets a minus sign. All right. So let's put together P1 and P2. Here we go. Okay, so the momenta, the first one, mass 0.05 kilograms times 1.7 meters per second. It's rightward. So that's a positive 0.085 kilogram meters per second. And notice that the units of momentum are just kilogram meters per second. We don't have a fancy scientific name for that unit in the metric system. You know, like for um, for a force we do, Newton. It's named after Sir Isaac Newton. But we don't have one for momentum. I don't know why. We have it for other stuff, but not for momentum. Now, P2, which we also need, that's an easy one because it's 0. It's because at position X2, the coin has stopped. All right, so we've got P2 and P1, and we now have everything that we need to figure out delta P. So here it is. It's always final minus initial, later minus earlier. So the final momentum is 0 because it stops, so that's 0.000 kilogram meters per second minus the initial momentum, 0.085 kilogram meters per second, right? And so that's a pretty easy one to calculate. Delta P is negative 0.085 kilogram meters per second, right? And notice that we have a minus sign there. Now that's going to come in handy because we're about to use the impulse equation. Here it is. F delta T equals delta P. All right, now on the left side, we already know what the force is, negative 0.020 newtons. Good. Delta T, we don't know what it is. That's what we're going to be able to find out because look, it's the only variable that we don't know in this equation. On the right side of the equation, we just figured out delta P, that's negative 0.085 kilogram meters per second. So we're golden. You know, we got it. You just got to do a little bit of division here. But before we go and calculate it all the way out, let me just point out that on left and right sides of the equation, there are minus signs. So you could actually cancel these babies at this point if you want, right? But I'm going to carry them over here just for a little bit longer, right? So here's the last equation, negative 0.020 newtons times delta T, unknown, equals negative 0.085 kilogram meters per second. That's my delta P. All right. Now, this is the impulse equation. This is what we just plugged in. Okay. Now we want to clear the left side. So we do that by dividing both sides by negative 0.020 newtons. All right. And I'm going to do a little bit of fancy footwork here. Notice that I've got delta T cleared on the left, so that's good. That's what I wanted to do. And I've got a quotient on the right, and we're going to compute that. But notice in the denominator, I don't have newtons. I have kilogram meter per second squared. But guess what? That's the same thing as a newton. And the reason I put it in that form, instead of just writing down newtons, is to show you that all the stuff, you can just look at it and see a lot of stuff that cancels. Kilograms, top and bottom, cancel. Meters, top and bottom, cancel. Per second cancels with 1 power of per second in the denominator, right? So that per second in the numerator and 1 power of per second in the denominator cancel, but you're still left with negative 0.020 per second in the denominator. But that's okay because per second in the denominator is regular seconds in the numerator. So you do your numeric part and you get 4.25. And then the seconds comes into the numerator, and there's your answer. And so in the homework problem, the question was, give me the stopping time to the nearest tenth of a second, right? So here's your answer, but now you want it just expressed to the nearest tenth. So it would be 4.3. All right, so that's a sample of an impulse equation used to figure out a stopping time. Now we're going to do some impulse calculations now, and these are styled as iClicker questions, which you won't have, of course, because this is an online class. But still, we can talk about it, and you can definitely study this baby. So let's take a look at the first one. It's multiple choice. You observe a large 4.5 kilogram blob of green jello floating in space with speed v equals 2.0 meters per second. A Klingon bird of prey vessel applies a 12 Newton tractor beam. How much impulse does the Klingon's tractor beam deliver in 2 seconds? All right. So we're trying to figure out F delta T. Now the F delta T that's applied to the jello, the force, we know what that is. It's 12 newtons right here. And the delta T, that's the interaction time. That's right over here, 2 seconds. All right, so we got the left side. That means that my delta P, the impulse, I just figure it out by multiplying 12 times 2. And so your answer is up here, 24 kilogram meters per second. Now, that's a basic, um, that's a impulse calculation. We didn't do a stop time or anything like that. Although we could, from the information that we have here, we could do that. The problem with that is um, the Klingon bird of prey is not trying to stop it. It's trying to bring it into its cargo bay or whatever. It's trying to capture it. So it's not going to try to stop it. Although maybe depending on their Klingon tactics, they might want to stop it and eat or something like that. I don't know if Klingons like Jello. Anyways, here's another question uh, related to this first one. Here it is. This one wasn't a clicker question, but it could have been back in spring of 2019. All right, how much impulse does the Klingon vessel receive from the green jello in 2 seconds? The green jello is not doing jack. The Klingon vessel is applying the tractor beam, right? But according to Sir Isaac Newton's third law, whatever impulse is delivered to the jello is also delivered to the Klingon bird of prey vessel, except in the opposite direction. So they get 24 newtons or 24 kilogram meters per second of impulse as well in the opposite direction. So really what the tractor beam is doing is it's inching them closer together. And usually the smaller object is going to move a little bit faster and further. But yeah, theoretically, the Klingon vessel does get some kilogram meters per second of impulse. All right, let's try another calculation. This one we'll do out in detail. A weighted basketball has a mass of 0.800 kilograms, initial speed of 22 meters per second. How many, so somebody's, throwing it down the court or something. How many, except it's a weighted basketball, so they're working out. They're using the weighted basketball to work out. Anyways, it's moving at 22 meters per second. How many seconds are required to stop it with a stopping force of 11 newtons? All right, let's get this figured out. We want to do F delta T equals delta P. We have the initial speed and the mass, and we're stopping it, so we have the final speed, 0. We have the stopping force, 11 newtons. So just like the example we worked out a few minutes ago, yeah, we can nail this. And so if you're doing this, go ahead and pause the YouTube, work it out. Okay, if you worked out, if you paused the YouTube and worked it out, this is your answer, 1.6 seconds. All right. If you didn't get that, let's work it out together. All right, we start with the impulse equation. F delta t equals delta p. All right. So on the right side, you have some momentum, 17.6 kilogram meters per second. And so there's my right side. And also the left side, we already know it's 11 newtons. And, just so you know, I've pre-canceled the negative signs. The negative sign would be applied to the stopping force because it's opposite to the direction of the velocity. So you'd have negative signs on both sides. So you may as well just cancel them ahead of time, which is what I did. And then just divide both sides by 11 newtons. And as before, we know that that comes out with seconds for the unit. And 17.6 divided by 11 is equal to 1.6. So there's your answer on that clicker question that you didn't click. All right, now at this point, I would ask the students in the lecture hall if they have a question about the calculation. And students usually have one or two questions. And you could hear them on the original lecture 11. But you can't ask questions in this lecture. So um, what I want you to do is what I want you to do is post if you have a question, post a new thread in discussions and ask, about this question. Like how did you get the denominators to work out right? Or whatever your question is. Okay. And you can do that as a strategy for every lecture and every part of the textbook as well. The discussions page is like, for us in the online class, that's like asking questions in lecture. Okay, except it's a little bit better because you type your questions out and I don't have to go, what? To hear your question. And it'll be there for everybody else to see. And so I'll answer your questions in discussions and everybody will benefit from it. All right, next topic, collisions. All right, now collisions, like a bunch of boxcars interacting, um, collisions in general are, like the next idealization of interaction. In other words, for the primary idealization that I've been stressing is the skateboarders. And you could call that a collision, I guess, but usually we just think of it as two skateboarders pushing off. However, if you have like two billiard balls colliding on a pool table, two box cars at the freight yard colliding and moving off at a different speed, yeah, you can think of that as another classic view of interaction. And so let's take a look at box cars, and they'll be our good example for collisions. All right, so in this particular problem, we're going to have four box cars. One of them is going to be moving, the one on the left, at 4.4 meters per second. Now the group of three over to the right, they're going to be stationary to start. And after they interact, they're all going to move off at a new speed, v subscript new. We're going to calculate that. The other factor that I've, put in here, a real boxcars out on the railroad are going to have slightly different masses, sometimes way different masses. But we're going to idealize this so each one is 35,000 kilograms, 35 metric tons each. So that's a good size for a boxcar, for the mass of a boxcar. And so the initial conditions are 4.4 meters per second for boxcar 1, 0.0 meters per second for the string of three. Now they're going to connect together, all right? So when they bump, they're going to interact and they're going to click together and they're going to move off to the right because the net momentum is still rightward. There's no leftward momentum in this system. And so they're going to move off to the right. It's going to be a little bit slower, right? And we're going to actually calculate how that works, how much slower that is. So, um, so our boxcar moves and it has a little bit of speed, V1, and that's going to give us some momentum, all right? And let's just write down the total momentum before the interaction. So this is initial momentum. The subscript is I here. All right. So we're doing P equals mv for the first boxcar, second boxcar, third boxcar, and fourth boxcar. For the first boxcar, the mass is 35,000 kilograms, and the speed is 4.4 meters per second. It's going rightward. Now the others are 0, 0, and 0 because they are at rest. So this one's pretty cinchy. You just multiply 35,000 times 4.4. And what you come up with is a pretty big number, 154,000 kilogram meters per second. All right, that's the amount of momentum that you have prior to interaction. Now in this situation, there's no net external forces, or there's no unbalanced external forces. So there's no impulse, there's no net impulse, all right? And that's because when they interact, when they click together, they each get the same size shove. You know, boxcar one is going to get a little bit of a shove to the left, and the three boxcars are going to get a shove to the right. And those shoves are those forces, they're the same size, they're just opposite directions. All right. So there's no change in the momentum. And because that is true, the momentum afterwards, P subscript F, also has to equal 154,000. Right? Now, we're not done calculating the new velocity. We're going to do that in a minute. But first, I have a question for you on the iClicker type question. Here it is. Why must the initial momentum state of the boxcars, P subscript I, equal the final momentum state of the boxcars, P subscript F? So there's my 1 and 3. And your options are because the mass of each boxcar is the same, 35,000 kilograms. B, because their interaction forces are opposite direction. Option C, because they exchange equal but opposite momenta, plus or minus delta P, left and right delta P. D, because there are external vertical forces, gravity and rigidity force from the actual rails. E, because the momentum is always conserved. And actually, E is the correct answer. This is a law of physics that momentum is always conserved. It's called conservation of momentum. So that means that in any interaction, without any external forces acting, like this one, or I should say without any unbalanced external forces acting, like this one, P subscript I and P subscript F are going to be the same size. All right. But here's another one that is actually just as good. The momentum states are equal because the boxcars exchange equal but opposite momentum, plus or minus delta P. So the moving boxcar, number one, delivers a little bit of rightward delta P to the three stationary boxcars. By Newton's third law, the three stationary ones, because they have mass, deliver a little bit of leftward delta P to boxcar one. And that's what actually slows down boxcar one. It speeds up the three stationary ones, but it slows down boxcar number one just to the right speed so that they all move off at a final speed together. So let's get back to that. All right, so as I mentioned, the momentum afterward has to be 154,000 kilogram meters per second. All right, now before the initial momentum state, same size, but all the momentum was in one boxcar. Afterwards, because of the interaction, they've all clicked together. Each one of those boxcars is going to have some momentum. All right, so this P subscript F, by conservation of momentum, we know it's 154,000 kilogram meters per second. But by definition of momentum, it's equal to mv1 plus mv2 plus mv3 plus mv4. All right. Now, and so in other words, mv for each of the four boxcars. But they're all moving at the same speed and they all have the same mass. So it's 35,000 kilograms times V nu plus 35,000 kilograms times V nu plus 35 kilograms times V nu plus 35,000 kilograms times V nu. So we got four of those babies. And what that adds up to is 140,000 kilograms total. It's like a big box car of 140,000 kilograms because they're all connected and they're all moving off at this one speed. Now we would say that that is true just because of the definition of momentum. All right. Now let me move this up a little bit. And now we have an equation we can solve for V subscript nu. If you look at that, all right, I can cancel kilograms left and right, or I can make my division here, divide both sides by 140,000 kilograms. And you can see kilograms cancel here as well, top and bottom. And then you do your division, 154,000 divided by 140,000, and that comes out to 1.1 meter per second. Now we're going to do another calculation together, and this is the point where I would ask the students, do you have any questions? All right. So, but you'll have time for questions in discussions, and saying you can listen to this lecture as many times as you want, so that's pretty nice. All right, so let's do a little calculation time here. Right now, this would be a clicker question in lecture, but for us, it's just kind of a study question in this lecture on YouTube. All right, same set of boxcars, but now my initial state for V1 is a little bit bigger, 6.4 meters per second. All right, and the group of three at rest again, 0.00 meters per second. All right, so what we want to figure out is the final state, V subscript nu. And so what you do here, what you'll do on homework if you have a problem like this, type in your answer to the nearest 0.1 meter per second of speed, and then hit the submit key, not the send key, but the submit key. I'll just pause. If you're working on this in real time, go ahead and pause the YouTube and try to work this one out. And I'll give you a few minutes for that. Okay, you've unpaused the YouTube. Did you get 1.6 meters per second? Hopefully you did. Now, if you missed on that, ask a question in discussions. Dr. B, how did you get that second boxcar question? Or how did you do the calculation? What was the denominator that you used? Whatever your question is. And but it's just like the one we just went through. The first boxcar question was 4.4. This one's 6.4 meters per second. So, but go ahead and ask that in discussions, and we'll talk it over. And just let me encourage you again: use the discussions as a virtual study group, and your classmates will chip in answers as well. I'll be chipping in advice and coaching you, and your classmates will hopefully be able to do the same. All right, so let's look at some of the formal statement of conservation of momentum. Now, the example that we've been concentrating on mostly is skateboarders, okay? And it's a great example of conservation of momentum. Now, here's the way um, it can be written in precise language. The total momentum of a group of interacting objects remains the same in the absence of external forces. And really that should be absence of unbalanced external forces. And the reason I point that out is because the boxcars have external forces, gravity, and the rigidity of the railroad tracks uh, acting on the boxcars at all times. But those external forces, they're balanced. They're not unbalanced. So otherwise, other than that, there's only interaction forces. When the boxcar one bangs into the group of three. So that's why momentum is conserved. And that's a statement without formulas and stuff, um, but just verbal of the conservation of momentum. Now, I told you that we get down to business with um, Einstein's four-dimensional space-time concepts. Let's get down there. Let's spend a few minutes on this before we close. Okay, momentum and energy in four-dimensional space-time. In the four-dimensional view of the universe that Einstein developed and other people with him, but he's the guy that got it rolling, you use for a geometric location, you have three spatial dimensions, but you also have to consider time, the temporal dimension, to be the fourth dimension. So you can't, for Einstein, you can't locate an object without also telling the time at which you're observing the object at a location. So location and the time of observation. All right. So that's four dimensions. Now here's the three spatial dimensions. And this is kind of a perspective view. So X, Y, and Z axis, they're mutually perpendicular. And so if the lectern is up in the front, this is for students in the lecture hall, big old lectern up in front. And so the Z axis goes straight up. That's from floor to ceiling. The Y axis goes from left to right across the front. And the x-axis goes from the front of the classroom to the back. And although it's right angles to the z-axis, you can't really walk along the x-axis because there's usually stairways in the lecture hall, except at the very bottom of the lecture hall. So this would be the three spatial dimensions. All right. Now the temporal dimension t is you would measure that with a clock, a watch, or a timer of some kind. Now, the dynamical quantities that encode interaction, potential for interaction, are similar to the positional description. All right, so momentum is the first part. All right, and momentum is mass times the spatial velocity. Vx, vy, vz. All right, even though we only usually work vx or vy. Sometimes we have vx and vy. Like with a baseball problem. So P is equal to mv, and the other component of the dynamical quantity is the energy. And as I mentioned, the example is for an energy equation is E equals mc squared. And in this chapter, we're going to develop something called kinetic and also potential energy. Okay, and those would go into this four-dimensional dynamical description that Einstein developed. All right, so here's my three spatial dimensions again. And here's my spatial momentum vector. So an x component, a y component, and a z component. And then the last component of the what we call the floor momentum is just the energy, whatever the energy is. If it's kinetic energy, if it's mass energy, E equals mc squared, whatever it happens to be, um, that's what that's what we've got, right? Now we're going to amplify some more on this in the lectures, and we're not going to get too fancy. This is about as fancy as we're going to get, but I'll be mentioning it throughout the semester, and we'll probably have a little bit of homework about it. Matter of fact, let me just give you a warning. We're at the end of lecture, and so after your exam one is done, you come back to study after exam one on September 25th. Uh, look for some homework.